Welcome everyone to another episode of Vision Basic. Before I get into the meat of this video, I just want to say thank you to everyone for their support and encouragement this past year. It's been a little rough in spots. I launched Vision Basic in May of last year, 2022, and it's been, well, I guess I didn't know what to expect really. I mean, I did have some expectations, but you know how that goes. I try listening to all the input everyone gives me, and I do take it all in and try to cater where I can. I work a regular job in retail, and I do all of this in my spare time. So I'm pretty much working all the time, including yard stuff. The 8-Bit guy made a video recently explaining the issues he has with merchandising, and it blew my mind. He really hits the nail on the head. With all the work he puts into it, he says he's making about $5 an hour. And again, that blew my mind because he sells a lot more stuff than I do. I'm going back into the negative, so I can't really give you an hourly rate yet. I'm going to post a link to his video though in the comments. It's really enlightening, so check it out. I did want to do some big splashy anniversary kind of thing, but the time just isn't there. Besides, the best way to celebrate the anniversary, in my opinion anyhow, is to work on improving the software. And I'll go into some details about that at the end of the video. So definitely stay tuned if you're interested in my tinkerings. And I'd like to say that I've been able to get to know some really great customers. Some of y'all have interesting lives, and I mean that in a good way. I don't mean like interesting, like with quotes. I wish I had time for good friendships with some of you, or pretty much all of you, but then I wouldn't have time for Vision Basic. So some of you are doing some pretty cool things with Vision Basic, and I get excited just to hear what some of you have been doing with the software. I thank everyone who has had kind words. All I can say is that I hope I've blessed many of y'all with this endeavor. I want to keep making it better, so I'll keep chugging along the best I can, okay? I certainly appreciate all the help from Marcio. Here's a shout out to you, buddy. He seems busy promoting all kinds of C64 and retro stuff out there. I wish I had his energy. Alright, so what is this video going to be about? Well, I had a customer who asked me if Vision Basic had a command for printing text to a bitmap screen. I explained that it didn't, and for a good reason, because each command added to Vision Basic becomes a part of the support library that ends up being output as a part of every compiled Vision Basic program. Now, if you avoid using any of the graphics and sound commands, Vision Basic will output a somewhat smaller portion of the support library into the compile stream, which helps. When coming up with a basic command set for Vision Basic, I had to decide which commands made the most sense for inclusion. I had to figure out which commands were absolutely necessary and which commands could be added later in the form of user-defined commands. The benefit of user-defined commands is that they only get output into the compile stream because they are added to the source code by the programmer, as the programmer sees fit. Vision Basic does come with an add-on set of user-defined commands and functions, which includes a circle command and other useful commands for drawing on bitmap screens, but there is no command included for drawing text on a high-res bitmap screen. So, I have come to the rescue with a fairly versatile solution. I call it the text command, a user-defined command for drawing text on a regular high-res bitmap screen. Some of you may recall that Simon's Basic has a command for doing this, but I don't remember all the features of its version of the command. For now, my version isn't designed for drawing on multicolor bitmaps, so Simon's Basic will have me beat there for the time being. My approach when creating this command was to include some of the special characters for changing character color and reverse status, and cursor positioning as well. Each 8x8 cell on a high-res bitmap screen can have its own plotting color and background color, so I also made a provision for being able to change the background color as well. The C64 has something called Extended Background Color Mode, which allows you to change a character's background color, but with significant limitations. but my bitmap equivalent allows for all 16 colors and the full range of 256 character shapes. Eat your heart out, extended background color mode. I whipped up a simpler version of this command in maybe 1 or 2 hours, I think, but it took a few days to add new features, reorganize the code, and optimize some things. So let's load up the first final version I came up with in the form of a demo. And let's list it. As you can see, the format here is simple, right up in here. You type the word text followed by a period, followed by an X coordinate, and then a Y coordinate, and finally a string that you wish to print. In this code here, I'm attempting to draw a couple playing cards to the bitmap screen to show that you can use the various graphics characters on the bitmap screen just like you would be able to do on a regular text screen. With the first card printed, the 8 of hearts, I simply placed red characters, including the spaces, on white backgrounds. And that's right here. With the second card printed, the 8 of diamonds, only partly available, I changed the character backgrounds to white as well, but I also used graphic characters around the edges, effectively shrinking the card somewhat. I also placed other text and symbols on the screen to show what else you can do with this command. And to show that the text has indeed been drawn onto the bitmap screen, I also have the program fill the outer edge with green bitmap lines. But let's just go ahead and run the program so you can see this for yourself. This isn't going to be a Rembrandt, so don't get too excited. Da-da-da-da. Like I said, not a Rembrandt. I could have gone all crazy with this, but then I would have had to take longer to get the video out the door, so. The main reason most people will want to be able to draw text on a bitmap screen is so that they can simply place text on a bitmap screen. Being able to place graphics characters on screen is cool, but you can easily draw lines and shapes with the regular bitmap commands. Now, if I press a key, you'll get to see something quite familiar to many of you. I know that 8-bit show and tell likes this maze generator kind of thing. But anyhow, this is on a bitmap screen, so. And press a key. And alright, let's list it again. I mentioned that you can change the background color of each 8x8 tile, but I didn't tell you how it's done. I decided to go with function keys because, well, it keeps things simple. I was going to go with the F1 and F3 keys, but they don't produce symbols that stand out as much against the other symbols, like, you know, your color symbols and such. So I ended up going with their shifted counterparts, F2 and F4. So if you look at line 71 above, you'll notice a couple symbols with some curve to them. The first curve, right here, which appears when you press F2, is for toggling from foreground to background. And the second curve, right here, which appears when you press F4, is for toggling from background back to foreground. So if you want to start having the background drawn in, say, blue, then you simply type F2 and press the appropriate key for blue. But if you want the text to be yellow, then you immediately need to press F4 and then press the appropriate key for yellow, and then start typing your text. So to set up 2 colors, foreground and background, you'll need to use 4 symbols, 2 color controls, and 2 function key presses. The function keys act like the keys for turning reverse mode on and off. They're just toggles. It can get a little messy in the logic if you employ all kinds of characters and color combos. But we're kind of used to that, right? Okay, let's press the space twice, and okay, so let's look at the routine for the user-defined command. I'm just going to highlight some details here. This won't be an in-depth look. In line 1000, I have additives to help convert the character codes over to poke codes. Each additive covers a set of 32 neighboring character codes. Most of the additives will force a wraparound on the byte level. The reason I went this route is to avoid having to select addition or subtraction. Going with all addition simplifies things in the code and generates faster results. The two values of 96, right here and here, are actually not additives, but rather indicators that the range of characters in question are control characters. And there's a good reason I chose the value 96 for this. It doubles as the machine language instruction RTS. So if you add this user-defined command to your own programs and forget to put in some kind of exit before execution flow ends up running into this code, it will force a return back to the basic editor. Did you catch all that? Okay. The routine entry point actually starts at line 1010. There is no tag for the values in line 1000 because we can use the text procedural tag instead and just subtract 8 from it. You can see this being done in line 1090 right here, text -8. In line 1014 we are copying the current high-res bitmap colors and placing them into variable CO. They are a combined set there, the two different colors combined together in a single byte. As each character is plotted to the bitmap screen, we will also be plotting both foreground and background colors. In line 1020, we are calculating the position where the text will reside on the bitmap screen. That's what the PS variable is for. And the variable CP in line 1030 is for the associated position within the color map. And RVS on that line is our reverse flag. In line 1050, we have to turn off interrupts and expose the character data in the character ROM. That might embarrass your machine, having all that exposed, but hey, you know, we gotta do it. Lines 1060 and 1070 fetch one of the characters in the string that gets provided by the command user. And line 1080 creates an index for our table of values in line 1000. Instead of dividing the index by 2 5 times, I instead chose to multiply by 2 4 times to the same effect. I went this route just to eliminate one machine language instruction and thus save some cycles. Call me frugal. We're trying to take our character value and divide it by 32 so that we can figure out which group of 32 characters it belongs to. Line 1090 fetches the value that converts our character code over to a poke code. If a 96 is fetched, we skip out to line 1400. Line 1100 applies our additive value to the character code and also handles reverse mode. In line 1110 sets up some pointers where we are going to copy the character data from ROM over to the bitmap screen. Line 1120 handles the color for the 8x8 square. And line 1140 copies the 8 bytes of character data to the bitmap screen. Notice that in this whole routine I do some programming in BASIC and some programming in machine language. I love having this flexibility. Line 1140 really needs to be in machine language because it's an inner loop of sorts. So, as mentioned in at least one of my previous videos, you want the inner loops to be fast and efficient. The stuff around the inner loops is less important. Not entirely, completely unimportant, but it's less important. Line 1150 advances the position sufficiently to help position the next character we wish to print. Line 1160 finishes out the rest of the string with a next. And line 1170 hides the character ROM and turns interrupts back on and exits us from the routine. In lines 1200 to 1280, we are converting color codes over to actual color values and merging the results with variable CO. This part of the routine handles both foreground and background color changes. There are a bunch of tags in lines 1200 to 1250 that we are using as entry points for jumps from further down the code. So if you look down at line 1450, right down here, you'll see that we are comparing to see if the control character extracted from the user supplied string is the code for red, value 28. If it is, we branch to the red tag in line 1220, right here, where we are loading the accumulator with a value of 2 for the actual color red. All those 44s you see in lines 1200 to 1240 are a programmer's trick, right here and right here. They represent the machine language instruction bit. This variant of the bit instruction is always followed by 2 bytes. So, whenever execution flow runs into the value 44, we are performing a bit instruction using the 2 bytes that follow. Since the bit instruction doesn't affect the value in the accumulator, it's relatively benign and simply acts as a skip for us. So, from just after the LDA number 2, in line 1220, we get to skip past all the other LDA instructions until we get to the LDX in line 1250. The reason to use this trick is more for saving bytes than anything. It's actually faster to issue a branching instruction, to be honest with you. But this trick, with a bunch of LDA instructions being followed by the value 44, is a quick way to pump out a bunch of code without having to worry about branching to specific line numbers and such. It just saves bytes. So again, if we end up jumping from here to here, the accumulator will be loaded with the value of 2, and then this 44 here will basically negate this, this instruction here. This represents bit, and these 2 bytes here, LDA and number 3, will basically do nothing to the accumulator, just perform a bit instruction. It doesn't even matter what these values are, it just happens and moves on. And then essentially this just keeps happening again and again and again and again and again, and until you get to about here. So that's just the quick and easy explanation. Now you won't want to use this technique in some, like, very time critical places. This is not like super critical, so it works, it saves bytes, and it's just, I don't know, I chose it. I could have just as well like did some branches here and skip over and whatnot, but it's not really something to worry about. Okay, in lines 1300 to 1330, handle the cursor movements on the bitmap screen. Lines 1400 to 1480 handle control characters from 0 to 31. The branch in line 1400 skips to 1500, where we handle the control characters that range from 128 to 159. The variable BGD in lines 1532 and 1534 is the toggle for whether or not control characters for color will affect the character color or background color. Right here, BGD. And now you've seen the whole program. So one of the benefits with Vision Basic is that you can write a program with basic commands and then convert whatever lines you wish into machine language. Using a line-by-line approach, you can actually convert pretty much everything into machine language if you wish. But if you're a beginner with machine language, this technique allows you to at least apply the knowledge that you have. Hold on, folks. Time for a little break.
I gotta pee. I believe he said he had to go pee.
Anyhow, I did create a version of this demo where I converted most of the code for the user-defined command into pure machine language, or actually all of it, maybe. I think so. Don't quote me yet. So let's load it up. And let's run it. This version generates some random numbers ahead of time for something you'll see soon enough, so that's why it takes longer to get to the graphics display. You'll notice that this version is almost instant when it comes to drawing the characters, which it's already done. It runs about 4 times faster, I believe, than our previous version, except for the line drawing part on the outside. You'll also notice that the corners of our second card on screen, the 8 of diamonds, have been rounded. Yay. I actually wanted rounded edges from the start, but realized that the Petski graphics characters don't include rounded corner pieces, so I had to create my own. But this isn't a problem with Vision Basic. So let's see the next part of the demo again, the maze generator. You'll notice that this part is faster as well. But if we generate the strings with machine language, we can get faster results. So check this out. And boom, there you go. Keep in mind that this is a bitmap screen. We can get even faster results if we skip all the overhead involved with a user-defined command, but that would mean not having a user-defined command, so I'm not going to go there. Finally, all those random numbers we generated at the beginning will be used for clearing the screen. Check this out. And voila. Alright, let's list things now, shall we? And I'm going to skip some things. Okay. Lines 200 to 280 draw the faster version of the maze pattern. Altering strings directly in Vision Basic is very risky, so you should not try to increase or decrease a string's length. Rather, just poke directly to existing characters in the string and you should be okay. So you can see in line 200 that we set up the full string with 40 space characters right here. And the lines that follow end up replacing those spaces with slanted line characters. The very first byte of a string in memory is its length. I'm just stating this for the curious. Again, don't change that. There is no easy way to get into the string field and simply toy around with strings and fabricate new ones with machine code. Playing around with the data will likely result in a crash at some point, so I'm just showing you the safest way to mess around. Anyhow, the space characters we have set up run from the 5th byte and onward, thus the reason for the LDY, number 5 in line 230. In lines 600 to 720, we are creating the rounded corner characters for our playing card. I'm simply writing over the square corner pieces. Line 600 copies the character set data over to character set 18 in memory. Now, character set 18 might seem like an awful place to try to put a character set, and this is because the computer will only ever see a ROM image there when it comes to displaying characters on a regular text screen. But in this case, we only need character set data for copying over to a bitmap screen, so the ROM image that exists at this location isn't going to impact anything. I live dangerously, folks. And this is the routine again that prints the characters to the bitmap screen. Aside from the passing of variable data, I believe everything from here on out is pure machine language now. Lines 1020 and 1030 show some original code in the form of rim statements. This kind of makes it into a rim statement here. And the assembly language beneath each of these lines is the conversion of these lines into assembly language. Notice that both lines 1020 and 1030 have the same expression of y times 40 plus x in them. It makes no sense to perform this calculation twice, so the results are copied so that they can be used in both of the calculations for screen position and color position. My work here has been optimized to the best extent that I can make it, so it appears a tad messy. So I'm not going to explain it all. I'll explain just a tiny bit though. In line 1022, right here, we are multiplying the y coordinate by 4 and then adding the original y coordinate to these results. And the effect of this is like multiplying by 5. So here we have we have ASLA and ASLA that's actually multiplied by 2, multiplied by 2. And then we're adding y again. And again, this is how we do times 5 quickly in machine language. The last ASLA brings things to a multiplication by 10. So by here we have, times 5, and then we're going to multiply it by 2 again. So in effect, we're now at the point of having multiplied the value by 10. In line 1023, we again multiply by 4 for both low and high this time, and this brings us to the goal of having multiplied by 40, which is what we are doing here. We add the x-coordinate to the mix in line 1024, and our calculation of y times 40 plus x is now complete. Anyhow, if you're proficient in assembly language, you can look over the code yourself to see what other conversions I've made. My goal was to eliminate all long branches, and I achieved that goal. Yes, I did. And now I'll go down to 3. I think I need to go down one more time. Okay. And here we are at the end again. To prove that there are no extra long branches, we can perform a list. I gotta get out of here. List. And if there were any long branches, they'd show up on the right side of the screen, right here. Nope, nothing. Not one long branch. Let's try it again. See? Nothing. Okay, so if you wish to add the text command to your own programs, in Vision Basic of course, you can merge it onto the back end of an existing program by simply loading it while your own program is resident in memory. So let's look at the actual file itself that you will be appending. And it's called text command. Here you can see that I've renumbered it. So as long as you don't have any existing lines of 60,000 or greater, you can easily add it to your programs. You can also place it in another program bank if you'd like, and by doing so you won't have to worry about conflicts with line numbers. What you see here are the command notes and instructions. The command detects which bitmap and color screens you are using automatically, so there's no worries there. Let's scroll down a bit. And you can pretty much delete all these lines up here with the delete command if you'd like. As noted in the instructions, you can change the CSET tag in line 61016 right here to point to a redefined character set instead of using the ROM version. You can also point to the lowercase set by changing the value here to 55296. You won't actually be pulling values from the text color RAM at this location, which that's what it is, but rather the character ROM for the lowercase set, which is also located here. So the color RAM and the character ROM both overlap at this point in memory. Anyhow, if you want to use a redefined character set, you of course need to create one and load it into memory first. Anyhow, the rest of the routine looks pretty much the same as what you saw earlier. I think this routine is about 487 bytes in size, if you count variable space as well. Not too hefty, for adding it to your own program. So 487, that's not too bad. Okay, so let's dive a little bit into how bitmap and character graphics are very similar. The layout for bitmap screens is very friendly towards being able to have character set data copied to it. But conversely, it's pretty darn hostile towards bitmap graphics themselves. If the bytes had been arranged sequentially along individual scan lines, our bitmap routines would probably run faster. So anyhow, let me show you what I mean. Okay, I have this screen split into two parts here by way of interrupt. The top part is a bitmap screen and the bottom half is a text screen with the full character set display on it. Once I press a key, you will see the characters being copied to the bitmap screen up top, byte by byte in sequential order, and on the bottom you will see the byte that's being copied highlighted by a thin line. This has all been slowed down for the purpose of the presentation so that you can see what's going on. So again, these are character graphics on a text screen. Up here we will see them being copied byte by byte up here into the bitmap area. Let's get it started. Now look at the top half and look at the bottom half. As you can see, the copying process is rather simple. And I do have some keys that'll speed it up a little bit for you. Let's go a little faster. Okay. But anyways, again, watch the line. And then down here you'll see a line. So each character, 8 bytes from top to bottom. And they copy just perfectly evenly from character set to bitmap set, or bitmap screen, sorry. And I know some of you are losing patience, so let's go faster. Let's go faster. Yay! Or I could just warp it. Okay. Okay, so I got a few more things to cover before I close this video. First, a couple tips, if you will. Some have been confused about how the loc command works, LOC. It does move the cursor to the location of your choosing, but it functions like pretty much every other print function. If you don't immediately follow it with something else, or at least provide a semicolon, a carriage return will be issued, making its use seem rather pointless. Let me show you. Okay. I'm going to run it. Okay. Now, some would expect the text to appear 10 places out from the left side of the screen, but that isn't what happened here. So people would expect this to be over somewhere over here. So there are two ways to rectify this. You go up to here and put yourself a semicolon. And then if you run it, this is what we wanted to see happen. The text has been placed 10 spaces down and 10 spaces to the right. Okay, list it again. Oops. But we can also just do this. You don't need the print command. So you don't need this guy here. Print, we're getting rid of you. But we still need the text, so we're not going to get rid of that. And now we'll run it. And there you go. And this is ideally what should have been done from the start. This command works no differently than if you had used space or tab. And I'll show you what I mean. See, you wouldn't do this here either. You wouldn't just print space 10 and then on a separate line put hello there, because these 10 spaces that it's going to print, it's just going to issue a carriage return. So keep that in mind when using the loc command. You either need to follow it with text or put a semicolon. And I've had a lot of people like comment in the forums about it, so I'm just figured I might as well show people here and save some people some trouble. Okay, so for another tip, a lot of people probably want to remove the spaces before and after a printed value. Vision Basic makes this easy with a simple poke, but let's start with an example. And run it. And as you can see, we don't have spaces here and here, but it has printed spaces before and after. Now we can make this statement false by adding the following line. And here's our secret poke. And then run it again. And now you see that the spaces have been removed. Actually, the second character is normally a cursor right, but there are some interesting things you can do with this trick. And I'm going to paste in something. Let's see. And run it. Here we are using color control characters to change the color of the digits. And as you can see up here, the 5 is the character code for white, and the 153 is to resume the normal light green color. And we can do this as well. And run it. Anyhow, all you need to do is plug in the design character codes into these registers 2126 and 2127, and you can come up with some pretty interesting things. I don't know, I mean, there's many different things you could do. You could put parentheses around numbers, whatever formatting you need, and it could save you from having to do it manually, in some cases. Like in this case, if you want all your letters to be white and all your text to be green, this poke here is a simple way to accomplish that task, and you don't have to keep using character color codes. Okay, so before I wrap this all up, I'd like to share what I've been working on lately. I'm trying to update Vision Basic with some improvements, but finding the time has been a little difficult. There was about a 2-month span between a couple of my recent videos, and the reason for this is that I had spent a few weeks working on one of the improvements. So my videos may get a little spaced out as I try to work on this, but I only have spare time to do all of this outside of my regular job, okay? Anyhow, I'll give some details on these changes. Okay, so I'm going to type as I say this. First, I've sped up compile time a bit. I'm not going to dish out by how much, but it will be gladly welcomed by all. Second, variable length will be improved. You won't be limited to just 8 characters anymore. So, there you go. Third, I'd like to add support for GeoRAM for Vision Basic. So, GeoRAM support. I don't plan to add any GeoRAM commands at this time, but I want Vision Basic to be able to use the cartridge as a form of RAM expansion. Since GeoRAM access is slower than RU access, I'm hoping that the improvements to compile time will make up the difference. Some people already own a GeoRAM or NeoRAM, so I know they'll be interested. Plus, you can buy NeoRAM cartridges for a very good price these days. I believe that NeoRAM is the term for modern reproductions of the RAM expansion. I still recommend RU memory overall due to its speed, but there are some benefits to GeoRAM over RU expansion. And lastly, I plan to improve a few commands and maybe add a command or two. Nothing super duper though. This is just an update and not an upgrade. I would also like to see if I can tackle some minor things in Vision Basic, so I'm just going to put MISC. The update will be free for anyone who has purchased Vision Basic already, so if you purchase it today, you're covered. Alright, so that wraps things up for this video. I'll be tinkering in the meantime, so I don't know when I'll have another video out. I don't expect to have the update ready like super soon. Like I said, I've already increased the compile time, but I haven't really done any of the other items. I have played around with trying to understand GeoRAM, so that's where I'm kind of at with it. I don't know, give me a month or two. I don't know. It's really up to how much time I can devote to this, so I either keep making videos or work on it, or I'm trying to do both, so that's kind of where I'm at with it. Anyhow, if you subscribe, you'll be able to stay in the loop on this project. So, as usual, I thank you all for watching my video. Please like and share, and definitely subscribe for more similar content. And make sure to visit visionbasic.net.